Hello everyone. Today we are going to explain how to use Buswell equation to calculate the amount of biogas that can be produced from an organic matter. First, we have to understand that the anaerobic digestion is a bioprocess that converts organic matter to biogas under anaerobic condition, which means that there is no oxygen. Buswell equation here is used just to predict the amount of biogas. The biogas here is mainly carbon dioxide and methane. Basically, the methane is a gas that we are interested in to have it as a source of energy, and carbon dioxide is also produced as a secondary compound there. Based on the composition of the organic matter, you can predict some ammonia or some hydrogen sulfide, but the simplest case here, we have an organic matter that composed of carbon, hydrogen, oxygen, and nitrogen. And based on the amount or the number of atoms or amount of carbon, amount of hydrogen, amount of oxygen, amount of nitrogen, we can predict how many moles of methane and how many moles of carbon dioxide. For this equation, here we have 1 mole of the material or the organic matter here composed of number of A for carbon, amount of hydrogen is B, amount of oxygen C, amount of nitrogen is D. And of course, we will have some kind of water there just as hydrolysis in the presence of course, we have anaerobic conditions here, anaerobic conditions in the presence of enzymes and in the presence of archaea, basically to convert the intermediate, and I will explain this maybe later, how anaerobic digestion is working. But just here, let's concentrate on this equation and how can we predict the amount of biogas that can be reduced. This anaerobic bacteria again, or anaerobic archaea bacteria, and of course we will have some kind of enzymes there. So based on that, we can calculate how many moles of methane, again, how many moles of carbon dioxide. If we have the number of moles from each gas, we can convert them to volume, right? If you have the molar volume, you can calculate how many liter or how many ml or milliliter of methane, how many milliliter of carbon dioxide, and how many milliliter of ammonia that can be produced under these conditions. If we have the number of moles of methane, number of moles of carbon dioxide, we can get also methane content. Basically, we can also methane. So for that, let's take this out here. So basically, let's just for a quicker. So basically, we always are interested in getting the amount of methane percentage-wise. So basically, if you have a biogas, because again, the energy source here is methane. If we need to get the percentage of methane, how many or what is the percentage of methane in the biogas, we can get it by, this is equal to number of moles of CH4 plus number of moles so number of moles of methane divided by number of mole of methane plus the carbon dioxide. So in this case, we have here CH4 plus number of mole of CO2. And of course, if you would like to have it percentage, you can multiply by 100. We'll see how we can do that in a second. So again, the first and the most important step is to get the composition of the materials that we are interested in. So basically, if we have food waste, if we have municipal solid waste, organic fraction of municipal solid waste, or other organic matter, so we have to analyze them for carbon, hydrogen, nitrogen, and oxygen, and then apply this kind of balance. So the next step is to have this kind of equation and get the number to be balanced. Basically, you have to balance the equation, and based on this balance, you can calculate how many moles of carbon dioxide, number of moles of methane, and again, we can convert this molar volumes, molar or moles to a volume based on the molar volumes. How can we do that? So I think maybe the best actually is to have just a very quick example here. How to do this. If we have this example, calculate the theoretical methane production. Here we have liter again. So liter means that we have to convert this moles. We have to convert the moles to liter. And to do this, we have to use the molar volume as well. Molar volume. Okay. To do that, we have 100 or 1,000 kilogram of organic matter of food waste with a chemical composition of CHON and the number of atoms for this carbon, or the ratio between different elements here are 3.7 of carbon and 6.4 of hydrogen, 1.8 of oxygen, and 0.2 of nitrogen. So, and then this to calculate how much amount of methane that can be produced. And the next step, what is the expected methane content? So basically, we have to do this balance and then apply this equation here to calculate how much, or percentage wise, how much methane in the biogas that is produced. Okay, assuming that the biogas consisting of merely methane, carbon dioxide, which means that just ignore this one. If you this basically the ammonia will be very minimal amount of moles, so we can just neglect it for simplicity here. Okay, let's as I mentioned, actually we have here, this is example here, we have the composition of the material. So the first step is to apply Buswell equation and make the equation balance. So basically just take this material here, C 3.7, H 6.4, O 1.8, and N.2, and then how many moles of water we can just apply again the Buswell equation here. So 4, and the A here is for this, in this case we have A equal to 3.7 and B, which is number of atoms of hydrogen in this material, is 6.4, and then B, and then C, the number of atoms for oxygen in this case, 1.8, and for D, which is number of nitrogen in this case, is 0.2. Okay, so taking these numbers and just replace these numbers here in this equation for Buswell. So 4 times A, 3.7, and B, we have here B 6.4, and then 2, basically if you look at this one here again, minus 2 times C is 1.8 plus 3 times D 0.2, all divided by 4. So basically we get how many moles of water will be reacted with the material in the anaerobic digester to produce how many moles of methane. Again, this is simple like what we did for the number of mole of water. So basically this is similar in this case. And then we can also calculate the amount of or number of moles for the carbon dioxide similar. So 4 here, this will have 4 times A minus B plus 2C plus 3D divided by 8. And this all give the number of moles of carbon dioxide. Again, we have only for the ammonia. In this case, we have just D times the NH3, or number of moles in this case for ammonia is 0.2 moles. Okay. After simplification, we'll have the material that is going to be treated with anaerobic digestion, and here number of moles of water will be reduced 2.125 moles of methane and plus 1.57 moles of carbon dioxide. Again, this doesn't actually change again because there is no other element in or other compound that is produced beside ammonia in this case. Okay. So now we have, this is just molar ratio. This is just based on the molar. In reality, we need actually to convert all of this to kilograms. So basically, we have to convert the moles of material to mass-wise in terms of kilogram or gram. So this means that based on the molecular weight of the material, which is 82.4 grams of the organic matter, can be reduced this kind of 2.125 moles of methane and 1.57 moles of carbon dioxide. So to convert this to volume, this means that we can have the molar volume, and we know actually from the ideal gas equation that 1 mole of ideal gas occupies 22.4 liter of volume under standard temperature and pressure. Okay, so in this case, we can calculate how many liter of material can be produced per gram Vs. Again, the gram Vs here, this is the organic matter. As we mentioned, the organic matter's composition is C 3.7, H 6.4, 1.8, and nitrogen 0.2. And all of this is just give the molecular weight is 82.4. This should be 0.4, not 0.8. Okay. After simplification, we will get 0.575 liter of methane per gram of Vs. Of course, we can calculate this again. This is just conversion this amount, which is 0.57 liter per gram Vs, which is similar to 575 liter per kilogram, right? This is basically, this also can be 575 liter per kilogram of Vs, right? Per kilogram Vs, correct? This is basically, if you multiply the numerator and the denominator by 1000 to give you this kind of sorry, you have to to multiply the numerator by 1000 and divide the denominator by 1000. So basically, you can get this kind of conversion here. So 575 liter per kilogram of gas. Okay. Okay. So again, this is just give you the amount of from a kilogram. Basically, this is give you the amount from 1,000 gram, 1,000 kilograms. So basically, you can get how many how much methane you can be reduced from this material. Okay. Okay, I think there is something wrong here. So 575 liter per gram Vs, which is 575 liter per kilogram. Yes. Okay. So again, so you get the idea here, and then you can get the composition, basically number of moles of methane divided by total number of moles of methane plus carbon dioxide. You can get the methane content here. Okay. So with that, I would like to stop here and